It's basically, if you want to, the ultimate control, this is the basis for the non-proliferation regime, is on nuclear materials. And some of us started in 2006 an organization called the International Panel on Fissile Materials. And this is related to that work that I'm going to talk about. And it goes all the way back to the beginning, to the first arms control proposal, which was by the Acheson-Lilienthal group. It was the proposal that the U.S. came to the first meeting of the UN in 1946 with, and the proposal was to put what the Acheson-Lilienthal group had called, and they were advised by technical people. J. Robert Oppenheimer was actually a member. They put dangerous nuclear activities under international control. And the three dangerous nuclear activities that they spotlighted were uranium mining, which is a little quaint now because at that point there were very few places where uranium was being mined. So that's obsolete. But the other two, I would argue, are not, to control uranium enrichment and plutonium separation. As I'll explain, actually, plutonium separation we can probably just do without altogether. And so then the issue will be to control uranium enrichment. This was already shown, well, Scott had a prettier version of that. This is just showing that since the Non-Proliferation Treaty went into force in 1970, the number of nuclear weapon states has plateaued. That's a very hopeful sign, but the issue is still with us of proliferation. We're currently engaged with both Iran and North Korea. So I'll talk about the proposal. I'll talk about the slightly modernized version of the Acheson-Lilienthal proposal, is to ban the production and use of highly enriched uranium. The two nuclear materials basically in all nuclear weapons. You could add maybe one or two more. But in practice, nuclear weapons use either highly enriched uranium or plutonium or both. The Hiroshima bomb was highly enriched uranium, that is uranium enriched in uranium-235. Today, weapons-grade uranium is defined as greater than 90% U-235. And plutonium, which is the material in the Nagasaki bomb. So the problem that Scott talked about was today we have these small, potentially small, but proliferation-wise significant facilities based on gas centrifuge enrichment. Oh, there it is. Okay. And this was supposed to be at the end. I put it at the end again. Okay, start with highly enriched uranium. There's actually, as Zia mentioned, there has been a proposal to negotiate a ban on the production of highly enriched uranium and plutonium and other potential fissile materials. Has been on the agenda, was endorsed by the United Nations in the General Assembly in 1993, but it hasn't gone anywhere. But then that would leave the question of producing highly enriched uranium for non-weapons purposes, and it is used for non-weapons purposes. But as I'll argue, that can be ended, and we've actually been working on that agenda. We being the international community. For 40 years, and made quite a bit of progress. Today, most highly enriched uranium, more than half, more than a third of the highly enriched uranium that's used annually in the world today is used by the U.S. nuclear navy in naval reactors, aircraft carrier reactors and submarine reactors. The UK basically depends on the US for technology, so whatever we do, they do in this area. And then Russia also uses, actually not weapons-grade uranium, but more than 20% enriched uranium in its naval reactors, and so it's in that. And Russia has been helping India. There are two other countries with nuclear submarines, France and China, and they both use low-enriched uranium. So the proposal is to make it a rule that countries should use low-enriched uranium for their naval reactors, and that would get rid of the largest use we have today. I won't talk about those. There are a couple of reactors in Russia that are fueled by highly enriched uranium. I will talk about the research reactor fuel use of HEU, and medical isotope is a small issue which is being dealt with. But we have managed in our activism to put this issue of converting U.S. Naval propulsion reactors to low-enriched uranium, and there's a group in Congress that has been pressing for such a program. On the research reactors, research reactors very quickly, people wanted to have high flux, high neutron flux reactors. You could make a more compact core with highly enriched uranium. So we converted to using highly enriched uranium, and then President Eisenhower gave his Atoms for Peace speech, and we started, the US and the Soviet Union started actually competing in trying to get other countries to see things our way, in offering as a gift a research reactor. And since we had switched to highly enriched uranium, they were fueled with highly enriched uranium. But after India used our assistance in the plutonium area to make their first nuclear explosion, we became more sensitive to the proliferation implications of shipping, which was several tons a year of highly enriched uranium. The standard metric today is 25 kilograms per bomb, sort of that round number that the IAEA uses. So we were exporting many bombs worth of highly enriched uranium to these research reactors all over the world. The Soviet Union was doing it to a smaller number of countries. And so we began a small program to convert these reactors to low enriched uranium. And then after the attack, after 9/11, Congress ramped that program up from in the single-digit millions of dollars a year to more than $100 million a year, and we started seeing real results. 33 countries have been cleaned out of highly enriched uranium. Their research reactors have been converted to low enriched uranium, and the highly enriched uranium that they had on site has been repatriated either to the U.S. or Russia. Russia has been cooperating in this program. Russia and we have been converting our own research reactors to low enriched uranium. There's only a few left, and Russia actually accounts for more than half of the highly enriched uranium fueled research reactors today. It's been pretty lackadaisical about converting its own research reactors. So that's now on the submarines. The challenge in the case of U.S. and UK submarines is that the holy grail of the naval reactor people has been lifetime cores, and they've just achieved that. The Virginia class, the latest attack submarine, the submarine can operate without being refueled for more than 30 years. In the case of the next generation ballistic missile submarine, it'll be more than 40 years. So the challenge is, when we talk to the Office of Naval Reactors, which develops these reactors, they say, well, there's no problem with the aircraft carriers. The reactors are so big, we would need a bigger core, but there's room in the reactor. The real problem is with the attack submarine, which is the smallest, it's 10-meter diameter hull, and we think that we would have to make an 11-meter diameter hull if you wanted to have a lifetime core with low enriched uranium. It'd be a bigger core. It's difficult to argue with them because the naval reactor design is more highly classified than the nuclear weapons design. But in fact, one bit of information somehow escaped them, which was the container in which they take the spent fuel and transport it to Idaho is licensed by the Nuclear Regulatory Commission, and the interior height of the container is 1 meter. So the cores are about 1 meter high. It gives you a sense of the scale here. And so the question is, and they also, as part of this discussion, which I've been involved with them since 1995, they've done a number of reports to Congress. And in the first one, they said, well, we would have to have a 3 times bigger core, volume-wise, if we went from 93.5%, which is weapons grade, which is what they use. They're operating on surplus Cold War highly enriched uranium from all the weapons we've dismantled. If we went from that down to 19.75%, just under the 20% boundary between low and highly enriched uranium. So the question is, can you fit it in? And we're just at the beginning of that discussion, early in that discussion. This just shows you the Virginia submarine. We're talking about the successor to that, which might come around in the 2040s. And I've estimated that maybe you'd have to increase the length of this. In the 1995 report, they said you'd have to have a 12% increase in volume, and if you move things around, I would argue that that we could be accommodated by a 12-meter increase in length. And in fact, it's a much bigger deal to increase the diameter of a submarine than the length. In fact, they're just starting to produce versions of this submarine now with a 21-meter section added for launching cruise missiles. So anyway, that's the state of the debate on that front. Now, we're dealing with Iran in the Iran discussion. For many years during the Bush administration, the mantra was not a single centrifuge shall spin in Iran. And it didn't work, and ultimately the Obama administration compromised and on the Iran deal that Scott described. But it does illustrate the problem of national enrichment plants that the Acheson-Lilienthal group recognized at the very beginning. And it would certainly be better if we didn't have national enrichment plants. And so this is the situation today with regard to the ownership of enrichment capacity. And I've made it in units of the amount of enrichment capacity needed per gigawatt of reactors. So Russia is the biggest. It has 220, it could support 220 gigawatts, much more than they have. They export a lot of that. Next comes France. Next comes China. And then there's URENCO. URENCO is a multinational. That's the alternative model. I mean, I think it's out of reach today to internationalize all these facilities, but maybe it's not out of reach to multinationalize them. And URENCO has facilities in Germany, Netherlands, UK, and in the United States, in New Mexico. It's interesting, there's a story, I guess I'll jump ahead. There's a story behind the fact that the US does not have a national enrichment plant today. In the Clinton administration, in the wake of the end of the Cold War, the US and the Russian weapon stockpiles were downsized tremendously. In the United States, we're at about 20% of the number of weapons that we had at the end of the Cold War. Those excess weapons contained a lot of highly enriched uranium. And so the naval reactors, for example, we're still working. We haven't produced any highly enriched uranium in this country since 1992. And at the current rate of use, it's going to last until the 2060s. So in the case of Russia, by the way, there was a deal. Tom Neff, who lives in this area, proposed this deal. We bought 500 tons. That is 20,000 weapons worth of highly enriched uranium off of Russia. And they blended it down to low enriched uranium, and half of the US nuclear capacity was fueled by that low enriched uranium for 20 years. So anyway, what happened then, we privatized the US enrichment complex. At that time, it was based on the kinds of huge facilities that Scott showed a picture of one, gaseous diffusion facilities, very energy intensive, not economically competitive. And the company that was set up, USEC, US Enrichment Corporation, worked desperately to try to stand up a centrifuge replacement for these facilities, and was supported subsidized for about 20 years by this US-Russian deal. But then at the end of the Russian deal, they went bankrupt. So that's why we don't have a national enrichment. It's not due to policy. It's not because they listened to me. But we are now in a position, if we wanted to be. Actually, I was involved way back in the Carter administration in ending the U.S. civilian plutonium program. And since that, the U.S. mantra has been to countries that are talking about separating plutonium, is we still do have the largest nuclear capacity in the world. we don't separate plutonium, you don't need to either. And in fact, no new countries have done that, although we're still arguing, as I'll show with a few. So anyway, we could similarly say, we don't have a national enrichment program, you don't need to either. There's still the issue for weapons, a military enrichment program, which is we're debating about. Oops. So, on the map, where do we go? On the map, there are 4 other countries with less than one, with smaller capacity too small to support a single 1 gigawatt reactor. And Argentina, Brazil, they were the debates we were in the 1980s. We were trying to shut down their enrichment programs. They were under in the 1970s as well. They were under military governments, and their motivation in building these enrichment programs was suspect. Argentina's is not operating, and I doubt it ever will. Brazil actually has continued operating, and Brazil looks like it will be the first country which has the first non-nuclear weapon state country which has a nuclear-powered submarine. It's been working on that for about 50 years, and they're getting, maybe in another 10 years they'll get there. So then there's Iran. We know a lot about Iran. And the other one is Japan, which also has a very small enrichment capacity, which has had an economically disastrous history. The current situation is that the big enrichers increased their capacity in anticipation that a lot more reactors were going to be built. That was before Fukushima, and there aren't a lot more reactors being built. And China is building some, but the global capacity has not been increasing. There have been as many retirements as there have been new reactors coming online. So we are over capacity. And in fact, the current prices of uranium enrichment services are such that they can just support the operations of the existing plants. They cannot pay off the capital cost of a new plant. So there's no real reason for these small countries to grow their capacity. And so, so what can we do? I've talked about, well, URENCO was founded because the Netherlands, UK, and Germany were all working on enrichment, gas centrifuge enrichment. They decided to get together, especially because the Soviet Union was very suspicious about the idea of Germany getting together, Germany building an enrichment program in that period. And in fact, the first plant was built just over the border in the Netherlands from Germany to sort of assuage the Soviet Union's concerns. But it's been quite successful and is one of the big ones. I told you this. Now, so here we have the current focus. One of the two current focuses is on Iran. The situation, but this is this larger situation in the Middle East. Iran has one nuclear power plant, one nuclear power reactor. Turkey well, there are 4 being built in the UAE, and the other countries are and there are a couple under construction in Turkey. Russia is building them. Saudi Arabia and Egypt are, well, Egypt has a sort of a draft contract with Russia, and Saudi Arabia is waving around billions of dollars. And one of the things Saudi Arabia is doing is it's refusing to the agreement that the UAE has with the United States that they will not have a national enrichment program. They will not have a plutonium separation program. Saudi Arabia says, whatever Iran can have, we can have. We're not going to give. And so we can see, and Turkey and Egypt have not, I don't believe Turkey or Egypt have signed such an agreement either. And so we could have a proliferation of the Iran problem in the Middle East. This is where I've talked to the Iranians and said, why don't you multinationalize and offer your neighbors and technologically other countries that have enrichment programs to join in your program. They say, that's very interesting, but this isn't a very good time. You haven't brought this up at a very good time, Frank. You know, the Trump administration, did you notice the Trump administration took the US out of the Iran deal? My idea would be to put it right in the Straits of Hormuz on one of the islands there. There are islands that are in dispute between Iran and the UAE. Okay, that's the highly enriched uranium story. On the plutonium story, the U.S. also caused a big proliferation problem early on with its enthusiasm for the idea of what Glenn Seaborg called. Glenn Seaborg was shared Nobel Prize for discovering plutonium and other transuranic elements, and he was also the chairman of the U.S. Atomic Energy Commission for 10 years during the 1960s. And so they promoted, for reasons that I'll explain, plutonium is going to be the fuel of the future for everything. And the U.S. was the world's leading nuclear energy power, and other countries said, well, we better not fall further behind the U.S. And the U.S. provided assistance under the Atoms for Peace program. And one of the countries that it was assisting in producing plutonium and then separating plutonium was India. And then, lo and behold, in 1974, India used some of the first plutonium it separated for what they called a peaceful nuclear explosion. So it didn't violate in their view, their Atoms for Peace commitment, but in fact, it did. What it resulted was in the U.S. was adult supervision. You know, the State Department and the White House got involved. What have you guys been doing in promoting separation of plutonium around the world? And so we reversed our policy. I mentioned that already, and then we tried to talk other countries out of it. Well, we succeeded in preventing other countries from joining this in the civilian plutonium club, but we did not succeed in talking everybody who was already in the plutonium club out of it, including India. And I just thought you'd be interested in this, in the basis for this dream of a plutonium economy. A gram of fission releases the heat equivalent of 3 tons of coal. The Earth's crust, on average, contains 3 grams of plutonium per ton. And therefore, the average ton of crustal rock has the energy equivalent of 9 tons of coal if you could fission it all that uranium. But only 0.7% of uranium is a chain reacting U-235, and that's the isotope is the primary source of energy in current generation nuclear reactors. A little of the U-238 is turned into plutonium by capture of neutrons, but not enough to make U-238 the fuel. Well, Szilard invented a plutonium breeder reactor in 1945, and which would actually be fueled by plutonium and produce more plutonium than it consumed, and therefore the ultimate fuel would be U-238. The only thing was that you had to use fast neutrons, and the water that the current generation of reactors use is very effective in slowing down neutrons, because when a neutron hits a proton in the hydrogen, it's like 2 billiard balls. You can actually, it'll lose a large fraction of its energy to the proton. So Szilard said, well, let's use liquid sodium. He was a theorist. Liquid sodium burns in air or water, and so when people built prototypes, they had lots of problems. And it turned out that the expectation, Szilard, when he was talking about this, he was imagining that the U.S. at most would be able to have 400 tons of natural uranium a year, be able to extract domestically and imported. And that would only support 2 gigawatts of light water reactor capacity. We have 100 gigawatts. We found lots more, many orders of magnitude more uranium since that time. And so today, the price of uranium, which is the whole point of economically of a breeder reactor, is about 2%, accounts for about 2% of the cost of nuclear electricity. The bulk of the cost is from the capital cost of the reactor, and these sodium-cooled reactors would be much more costly than water-cooled reactors. And since they wouldn't work most of the time, they would generate because of the sodium problems, they would generate many fewer kilowatt hours per dollar of investment. So they never have, well, we still have, Russia has 2 operating prototypes, but they don't argue that they're economic. No, so the problem, of course, was that the plutonium is a weapons material, and what the Atomic Energy Commission was imagining was the world was going to be based on a weapons material, and Szilard recognized, he says, well, that problem, and he says, maybe we need peace before we can have breeder reactors. And can we? And he said it better. I don't have the exact quote, but anyway, he recognized the problem. But just as with a military base or with a nuclear weapons lab, once you start it up, it's very hard to shut it down economically. And so 4 countries have continued separating plutonium, even though the breeder reactors didn't come, and they have had various strategies for dealing with the plutonium, these 4 countries. And you see that the civilian, this is not there's in addition, there's another 250 tons or so of weapons plutonium we produced during the Cold War. The civilian plutonium stockpile has been growing even because in part because there are no breeder reactors to use the plutonium. UK is finally stopping and trying to figure out what to do with this plutonium. France decided to recycle it into light water reactors, which is and the fuel that they're producing to replace the low enriched uranium fuel only costs 10 times as much as a fuel that they're saving. So ultimately, the gravity of economics should bring it down, but there's a lot of staying power in a bureaucracy. Russia still has the idea of breeder reactors, and hasn't been using any. It's actually the prototype breeder reactor that they built in 1980 and have been operating since then is fueled by highly enriched uranium, because they didn't want to get into the complications of plutonium. And now they've actually built another prototype which is going to be fueled by plutonium. But so in the meantime, they've been piling it up. And then Japan would like to do what France is doing, but hasn't been able to make the plutonium recycle work there. So I'm just, the lights turned red, so I'm just going to go to the summary here. And so we should design our submarines to use low enriched uranium fuel, and then we could ban the production of highly enriched uranium. We should move toward multinationalizing enrichment. And since plutonium separation is unnecessary and uneconomic, we should ban that while we're at it. And then finally, if you're interested in more information on the fissile materials, the International Panel on Fissile Materials website is fissilematerials.org. That exists, unlike President Trump's and the Iran deal now website. Yesterday, Stuart Prager gave talked about an initiative to start self-education of the physics community, again, on these nuclear weapons issues, and then with that education, start the education of Congress, which is used to know something about nuclear weapons policy, but since the Cold War, that's gone way down. And so without Stuart's permission, I've put his email address up there, and also mine. I'm involved if you especially if you're a young person, are interested in getting involved. So thank you.
Well, we're just slightly over time, but this is the last session, so I think we can have time for questions and discussion. Anyone who'd like to ask a question, please go to the microphone.
Quick question. I'm wondering, do you have like an idea of how the Middle East situation is going to play out over the next 10 years?
Which situation?
The Middle East.
The Middle East.
Yeah.
I guess Iran, Israel, Saudi Arabia. I noticed actually that Jordan was yellow on your map. I was a little puzzled by that.
Yeah, Jordan is interested. So it's time to get ahead of that problem. And unfortunately, the U.S. getting out of the Iran deal was a real setback in terms of actually making progress on preventing an arms race in the Middle East. But we're working on it, but we don't have the answer.
Hello. So I'm just curious how the 20% mark was decided to define highly enriched uranium, and I was wondering if there's also been any discussion on resetting or redefining that mark so that other levels of enrichment aren't categorized in the same way as weapons-grade uranium.
Yeah, Alex Glazer, I don't know whether he's still here, wrote a paper about that. But basically, the critical mass goes up very quickly as you go to low enriched uranium, and in their wisdom, I think it was in the 1960s, basically the U.S. Nuclear weapons experts thought that was a good place to draw the dividing line. There are people who, the mass only goes to infinity at 6%. So you can argue within that range. about it, whether it would be whether we have to worry about weapons being made out of less than 20% enriched. It's a fast critical mass that we're talking about for an explosion. A fast neutron critical mass. Okay. Should we declare
Any other
victory?
questions or comments? Stuart Prager, would you just stand up and introduce yourself, since Frank mentioned that you're... so Stuart is going to be the chairman of the Forum on Physics and Society in 2 years. And he's been developing this proposal that Frank mentioned to educate physicists and get them more involved in nuclear weapons policy. Basically, the point that several people have made, that we're no more secure now from the threat of use of nuclear weapons, for example, because of the hair trigger alert, than we ever were. And maybe actually even in worse shape, because people just don't understand how dangerous they are.
Did you look for that at that website?
So I want you to stand up, Stuart, so people, turn around so people can see you. Okay, well, if there are no further questions, farewell to all, and let's thank all the speakers in the afternoon session.